In today's lab video, we are going to cover proton NMR spectroscopy. And we're going to switch in a second to PowerPoint slides. And after viewing this video, you will be able to go into D2L and check out the proton NMR spectroscopy assignment, where there are a bunch of proton NMR spectra for a given organic compound, and you are to characterize or determine the organic structure based on the molecular formula and the NMR spectrum for that compound. So we're going to transition over to the PowerPoint slide, and we are looking at nuclear magnetic resonance spectroscopy, and we call this NMR. NMR for nuclear resonance. Nuclear magnetic resonance. And there's some nuclei that we look at. For organic molecules, we're going to focus on proton NMR and C13 NMR. So we have proton NMR and C13 NMR. And when we say proton NMR and C13 NMR, we're saying that in a proton NMR, we are getting signals from protons, from hydrogens in the organic molecule. And we can tell something about the structure based on the signals. In C13, we're getting signals from C13 atoms or nuclei in the molecule, and we can also say something about the organic structure based on the signals we get from a C13 NMR. There's nitrogen and fluorine and phosphorus NMR, but we're not going to cover that. That would be more of an advanced topic in organic chemistry. But we're going to focus on proton NMR and C13 NMR. And the first one we're going to cover is proton NMR. Next lecture, next lab, we'll focus on the C13 NMR spectrum. So there is a rule that to use NMR, the nucleus has to have an odd atomic number or an odd mass number. If it has an odd atomic number or an odd mass number, or both, it has what's called nuclear spin. Let me highlight nuclear spin here. So check out a proton. All right. If I have hydrogens, I'm just going to draw an alkane. If I have hydrogens in this molecule, H's, right, on different carbon fragments, these hydrogens have nuclear spin. Why? Well, hydrogen has an atomic number of 1. There are isotopes of hydrogen. You have protium, which has a mass number of 1. You have deuterium, which has a mass number of 2. And then there's tritium with a mass number of 3. So when you look at this symbol I give for hydrogen, I show an H, which is the symbol for the element hydrogen, and then superscript 1 says something about the mass number. In the periodic table, in a box or in a little square, you have the element symbol H or C for carbon or He for helium, whatever. And above it, directly above it, you see an atomic number. Well, if I were to show the atomic number in the symbol that I show to the right here, I would show it as a subscript down here. Now, it really doesn't make sense for me to show the atomic number and the symbol because it's kind of redundant. So what I do is I say that this is hydrogen, so I know if it's hydrogen, it's got 1 proton in the nucleus. So whether it's hydrogen, deuterium, or tritium, the atomic number is always 1. So I really don't need to show this guy. It's kind of redundant. I don't need to show the atomic number because I know I'm dealing with hydrogen. I know hydrogen has one proton in the nucleus. But it is important at times to say what isotope you're dealing with. If you have hydrogen and the mass number is 1, this is called protium. If you have hydrogen, mass number of 2, that isotope is called deuterium. And sometimes you will see a D instead of the H with a mass number of 2. And then tritium is T. So what we're saying here is when you show the element symbol H, that's already telling you how many protons or what the atomic number is. We know hydrogen has always got one proton in the nucleus, and since it has one proton in the nucleus, atomic number is 1. All right, so does hydrogen have nuclear spin? Well, all isotopes of hydrogen have nuclear spin because they all have an atomic mass number of 1, which is an odd atomic number. Now, I said atomic mass number, pardon me. All those isotopes have an odd atomic number. Some of these isotopes also have an odd mass number. Protium has an odd atomic number and it has an odd mass number. Deuterium would have spin because it has an odd atomic number, but it does have an even mass number. But it doesn't matter because one of the two is odd, and that gives that atom or that nucleus a nuclear spin. We're really not going to be so concerned about tritium. Now, if you look at proton NMR, we are only focused on the protons. I'm going to circle these guys in my molecule. And that NMR instrument, and we'll talk a little bit about the NMR instrument here in a second, gives us signals. And from those signals, we can determine how many different types of protons we have in the molecule. Sometimes we can determine number of protons. And we can also get some information about, how many proton neighbors a proton has. And we'll talk about all this stuff. And all this will lead to us being able to determine the structure of the organic molecule. If you look at carbon, and I'm going to put carbon down here, has an even atomic number. And there are some isotopes of carbon. There's C12s, that's the most abundant of the carbon isotope. And there's C13s. Well, if you're a C12 atom, you have both an even atomic number and an even mass number. So C12 atoms do not have nuclear spin, but C13s do. C13s have an even atomic number, but an odd mass number. And because it has an odd mass number, it has nuclear spin, and we can get a signal from that nucleus, that type of nucleus, in the NMR. So when we test you on all this stuff, we're not going to test you on the theory behind NMR. But I'm going to give you just a little bit of background, which will sort of lead us to looking at a spectrum and being able to interpreting that spectrum. And it'll allow you to interpret the spectrum and come up with a structure based on the spectrum that you see. So if you have a nucleus, the spinning charged nucleus generates a magnetic field. So here we have a couple of different things, a couple of different pictures here for you. We have a spinning proton, so imagine an atom. So we have these plus charges, these are protons inside an atom, so we just kind of give you a little boundary there for the atom. And if you have spinning proton, right, in a nucleus, this generates kind of a magnetic field. And that's what these arrows represent. They represent a magnetic field right here. Much like if you had a bar magnet. Check out this bar magnet here. See this? The north and south ends of the bar magnet, the poles, right? Bar magnets have a little magnetic field. right here. This is the magnetic field that's represented for this bar magnet with these arrows. And then there's this loop of current deal. But we're going to focus more on the atom, which have this spinning proton, which generates a magnetic field. And from that, we can get a signal if we put that nucleus in a larger magnetic field. So what we're going to have in an NMR is we're going to have an instrument that has a magnetic field that feels the little magnetic fields coming from these H's and these C's in the molecule. And from that, we can generate a signal, and we can say something about the structure of the molecule. So what we're going to do is we're going to compare atoms. We're going to compare nuclei like hydrogen, protium, and C13 to bar magnets. Now, atoms aren't bar magnets, but like bar magnets, they generate a small magnetic field. So these guys, it's kind of an analogy. We'll use that bar magnet as an analogy. So this is our atom right here. Say it's a proton or a C13, whatever. And like a bar magnet, our atom, these protons, will generate a small magnetic field. Now you can represent a magnetic field by doing this. You can do like a little weird looking arrow. So a proton has a little magnetic field. If you have a large magnetic field, your arrow gets larger and bigger. Okay? So what we can do is we can put these little bar magnets or these little atoms that are in molecules in a large magnetic field. All right? So if you had a big magnet, this is our big magnet right here. See this big C-looking thing? This is kind of a representation of a very large magnet. And then you see this arrow right here. They show one arrow, that's fine. You could show two arrows. It doesn't matter. But this green arrow here is representing the large magnetic field that this big magnet right here generates. So if I have a really big magnet, right, it's going to generate a really large magnetic field. If I take a little bar magnet that I can hold in my hand, right, this other thing, maybe it's not something that you can hold in your hand. It might be really big and heavy. Thus, it would create a very large magnetic field. But if I take that very large magnet and I put a small bar magnet, take the bar magnet, hold it in my hand, and put that bar magnet in the large magnetic field, what's going to happen? Well, we know that if you take two bar magnets and you bring them close together, there's some attraction. And if you twist the bar magnets in such a way as to align the north and north poles together, you get some repulsion, right? So if this arrow is representing my magnetic field, that's the external magnetic field of the big magnet. That bar magnet also has a little magnetic field. See this arrow here? It should actually be really small, right? So I have something that has a small magnetic field inside a very large magnetic field. So these arrows here are for my very large magnetic field. I'm going to try to thicken those up. And I got this little guy that has a really tiny magnetic field. I could take that little magnet and I could hold it with my hand inside the large magnetic field. What is that little magnet going to want to do? It is going to want to align the little magnetic field with the big magnetic field, right? And the big magnetic field is going to be like a bowling. It's going to say, align with me. and force that magnet to align with the external or that very strong magnetic field. You could try to reach in, grab the bar magnet, and twist it, but it would be really hard to do. Probably impossible to do if this magnetic field were strong enough. If you tried to twist that bar magnet, right, from this position here, which is the low energy, more stable because it's aligning with, and kind of make it neutral, if you let go, what's going to happen? The bar magnet is going to align with. It's not going to align, it's not going to oppose. It's going to automatically align with, because that is the lowest energy conformation for that bar magnet. You could try to force that little bar magnet to oppose the external magnetic field, right? So there's that big external magnetic field, and I'm going to take that bar magnet and I'm going to have it aligned so it is opposed. So its little magnetic field that it generates is going to where it is opposing the big magnetic field. Well, this is going to take lots of energy to force it that way, right? So you would have to be very strong, and you would have to bring lots of energy into that to force that to oppose the magnetic field, the external magnetic field. And what's going to happen if you let go? Floop, it's going to flip and align back with that magnetic field. So what we know is that if you take something that generates a little magnetic field, like a small bar magnet, which has a magnetic field, and you put it inside a large magnetic field, that bar magnet has two options. It can either align with or oppose. If it aligns with, it's stable, it's low energy. If it opposes, that costs energy, and you have to put energy into it to go up in energy, right? If you have an atom that has a small magnetic field like the bar magnet. So instead of a bar magnet here, I'm going to have an H, right? I'm going to have a proton inside this atom, and it has nuclear spin. And it also has, see this little arrow here, a small arrow. It has a small magnetic field that it generates. And I can take that proton, no, I didn't want to do that. I can take that proton and I can put it inside a magnet that generates a very large magnetic field. And like the bar magnet, those atoms, those nuclei, can either align with the external magnetic field, or they have this other option, right? External magnetic field, really horrible picture of a magnet, and then there's my nucleus, whatever I want it to be, a proton or a carbon. I can put my molecule, which has these atoms, in the external magnetic field. These atoms, if they have spin, protons do, hydrogens, protons do, they will have two states that they can be in. They can be in an alpha state, which is lower in energy. So if this is potential energy and you have high and low, the alpha state, the alpha spin state, is lower in energy. And then you have a beta spin state. I'll just say state, beta state, alpha state. But it should be alpha spin state, beta spin state. If I want, I can pump some energy into this, all right? And I can get this to jump from a low spin state to a high spin state. So what we are going to do in proton NMR spectroscopy, in that proton NMR, what you can do is you can irradiate that with radio frequency. You can hit that molecule that contains these nuclei with radio frequency, and that radio frequency allows the protons to flip spin states, right? So if I pulse this guy, if I give it energy, right, it can change spin states from the alpha spin state to the beta spin state. But what's going to happen when it goes from alpha, where the proton has its magnetic field, the little magnetic field aligned with, to it flips to the beta spin state, where the magnetic field is now opposing. When it doesn't get any more energy, it's going to automatically do that. And from that, we get a signal. So we're not going to go into the physics of it all, because that's pretty much what this is. We're just kind of giving you a little bit of background to say, okay, so if I put certain nuclei in a large magnetic field, and I give them energy, I get a signal. And this is how we get this, kind of how we get this signal. It's the simple explanation. So again, we can have another picture. Say we have, and sometimes people get confused by this. What are these? Well, since we're looking at organic molecules and we want proton NMR, imagine these are atoms that are hydrogens. And here we're kind of just seeing them kind of separate. You might have a carbon that connects these three hydrogens. I don't know if this is even going to be that good of a picture. Let's do this. And then you might have another carbon down here that connects these three. Something like that, right? So these nuclei that we see, these circles with the little green arrows, what we're saying is we have a hydrogen, and that's an atom, and in this atom you have protons, has an odd atomic number. Protium has also an odd mass number. So they generate a little magnetic field, and I can show that type of arrow or this type of arrow for the small magnetic field that this nucleus generates. So here we have nuclei. We, in this picture, really don't care what type of nuclei these are. So I'm going to erase this. I'm going to just draw an H in one of them. All right. I could have a C13 here as well. So if I take these guys that are outside, no field, outside the magnet, their little magnetic fields are going to just be aligned however. It's going to be very random. But I can organize what's going on by applying an external magnetic field. I'm going to put these nuclei that are actually attached to other atoms, they're in a molecule. I'm going to put them in a very large magnetic field. So there's my large magnetic field. So the molecule is now in a magnet, and it's inside a very large magnetic field. So all those little protons or all those little nuclei that are in your molecule are now in a large magnetic field, and they only have two options. They can align with that external magnetic field, that's the alpha spin state, or they can oppose and align to where they're opposing the external magnetic field. But there's no in between. There's no like randomness, right? It's either this or this. And if you want, you can give these guys enough energy, right? You can, instead of grabbing the bar magnet and twisting it to oppose it, right? You pulse these things with radio frequency, and that's enough energy to spin flip it. And that spin flip, right, will cause the low energy spin state to flip to a high energy spin state, and then automatically that nucleus in that high energy spin state will flip back down because it's high energy, right? So if you jump up in the air, you go from low potential energy to high potential energy, what's going to happen? Automatically, you're going to come back down to the ground. So if you give this enough energy to go up in energy, it will automatically go down in energy, and from that you get a signal. But you have to have everything in a very powerful magnet. Here's another way to show the thing, right? So we talked about the spin states. There's the alpha spin state, low energy, more stable. Here's the beta spin state. So there's the external magnetic field that your magnet would generate. This is some kind of nucleus. We can call these hydrogens. If I take this hydrogen that has a small magnetic field, that's that little green arrow representing the small magnetic field because this nucleus has spin, and I'm putting this in a larger magnetic field, so I get a very big magnet, put this nucleus or nuclei in a big magnetic field, large magnetic field, and it has two possible spin states, an alpha, low energy, and a beta, high energy spin state. And I can have it do this spin flip deal. I can go from alpha to beta if I give it enough energy. That's kind of like you going from low to high, right? If you want to go up a hill, you got to put energy into walking up a hill or maybe being dragged up a hill or pulled up a hill. If you want to go back down a hill, then you're releasing energy, right? You're going from high energy to low energy, and that's kind of automatic or spontaneous. And again, these nuclei that we're putting in the magnet have two options. If we give these nuclei energy, they can go up in energy to the beta spin state, and then they will automatically go back down, and we can measure that amount of energy, that energy change, and that turns into a signal in the proton NMR spectrum, and we can learn something about the environment that those protons are in. So we're going to go on to something called magnetic shielding. If all protons absorb the same amount of energy in a given magnetic field, not much information could be obtained. But protons are surrounded by electrons that shield those protons from the external magnetic field. So there's this thing that we're going to talk about called shielding. If I have an organic molecule, let me see. I'm going to draw my little picture of my organic. Here are my carbons. Now check this out. Those protons in my organic, if I'm looking at proton NMR, right? These guys are going to be the ones that generate my signal. And I will get a signal for these protons. Why? I'm going to take my molecule, whatever this compound is, in this case it's 1, 2, 3, 4, 5, pentane. I'm going to put it in a little glass tube, drop it in the NMR, which means I drop the thing into a large magnetic field. And these little protons, right, I'm going to circle them, have nuclear spin. So they generate a little magnetic field. Now, these protons are equivalent, right? Remember equivalent groups we talked about in Organic 1? If you have two carbon fragments that are equivalent, those protons will be equivalent. So the ones in blue here on this methylene are equivalent to the ones in blue on this methylene. And the methyl group on the end is equivalent to the methyl group on this end. So I'm showing protons in black, protons in blue, and protons in red. And there's actually 6 protons in black. They are all equivalent, meaning they are all shielded exactly the same. So if you take a hydrogen, right? I'm going to take a proton here. And you put that proton, I don't know why I did that, there we go, in a magnetic field. So there's one in blue, there's one in black. You can even have one in red. If you put all of these protons in a magnetic field, and they're just protons, they would all be shielded exactly the same. But if you take these protons and you put them in different environments, right? Now they will not be shielded the same. So what we're saying is this proton and the other ones that are exactly like it are going to be shielded differently than the one that you see in blue and the other one in blue like it. And the one in the 3 in black, the 2 in blue, and the 2 in red are not, like these two are equivalent because they're on the same carbon. So they are chemically in the same environment. They have the same amount of electrons, right? This molecule here is made of atoms, which is made of electrons. If you have electrons around your nuclei that have this little magnetic field, they're shielded from the external magnetic field that you put them in. The more electrons surrounding the nuclei, the more shielding you get. The less electrons, the less shielding. And when these protons are shielded differently, they give you a different signal in the NMR spectrum. And from those different signals, we can learn what environment those protons are in, and it will tell us something about the carbon fragment that they are on. Is this proton on a carbon fragment that is an alkane-like carbon fragment, or are they on an alkene? Let me see here, like carbon fragment, which in this case, these protons would be very different from the other ones that we drew in earlier. And they would also have magnetic spin. So now I have protons in black on carbons that are alkyl carbons, right? I have a methyl group, an alkyl group. I have a methylene group, which is kind of like an alkane type fragment. I have another methylene, which has 2 protons that I've labeled in red, alkane-like fragment. And then I have a proton in orange and then 2 protons in green that are on carbons that are a part of a carbon-carbon double bond. So these are alkene-like carbons. And remember in IR, the CH of an alkane versus the CH of an alkene are different. In NMR, same deal. The CH of an alkane will show up in different locations in the NMR spectrum compared to the CH of an alkene. So alkane CHs have different values, shift values, we'll call them, than alkene CHs. So because of this different shielding, we get information about the structure. In my NMR spectrum, I can tell whether I have hydrogens that are alkyl-like hydrogens, alkane-like hydrogens. I can also tell whether I have alkene-like hydrogens on a carbon-carbon double bond, hydrogens on a carbon-carbon triple bond. I can tell whether those hydrogens are on an aromatic ring, and we'll go over all of those. So it's really interesting with this shielding here that you get these different, you would get different types of signals. This is talking about shielded protons. So again, we're looking at representation here of this external magnetic field, and this is our little proton that is inside the external magnetic field. And that small black arrow is representation for the small magnetic field generated by the small nucleus atom in the large magnetic field here, right? And this thing can spin flip. So how much energy is required for this to spin flip, right? Because we're going to actually irradiate this with some kind of radio frequency to make it spin flip. And it's going to absorb that energy and flip, and then going to flip back and create a signal. If this was kind of a naked proton, where there was no electrons around it, then it would feel more of that external magnetic field, and it would cost more energy to spin flip it. But if you take that proton and you put other things around it, this blue halo type of thing represents, say, a cloud of electrons around our proton. In a molecule, you're not going to have a blue halo. You're going to have a proton, a hydrogen, with other groups, other carbons, other hydrogens, maybe oxygens, nitrogen, whatever, around it. So that's kind of what that is representing. If you shield this, then to spin flip it costs a different amount of energy. And it requires more energy to actually spin flip it because it's not feeling as much of that external magnetic field. So what we're saying here is that protons that are more shielded, have more electrons around them, require more energy to spin flip than protons that are less shielded. So they will show up in different locations in what we call the NMR spectrum. And because of this, we'll be able to see how many different signals, which will tell us how many different numbers of protons there are. Case in point, this molecule here, very simple molecule we're going to go to. So don't get hung up on this slide too much. Let's talk about a real example. This small molecule here, methanol. I have a CH3OH. That's my condensed. I can turn this into a skeletal structure. There you go. Where this is a CH3 fragment. I could also turn this into a 3D structure. So there is the methanol molecule right there. Now, how many protons do we see? Because we're going to be looking at proton NMR, right? So we are going to put methanol. So I take a drop of methanol. Methanol is a liquid. It's a clear, colorless liquid. And I'm going to put it in a tube. So if I put a drop of methanol in a tube, and I'm also going to add something called NMR solvent, which we'll talk about, and I put that in an external magnetic field, I have countless numbers of these small molecules in a tube that is in an external magnetic field. All of these molecules have protons, right? There are 4 protons per methanol molecule. These protons are not equivalent. The protons on the methyl fragment are equivalent, but they are non-equivalent to this guy here. So I'm going to show that proton on the oxygen in red. And I'm going to circle it. The red proton that is attached directly to the oxygen is shielded differently than the 3 protons that are equivalent that are attached to the carbon. So if you look at the shielding, the proton in red is less shielded. Why? Because of induction, the electrons in this bond are being pulled towards the more electronegative oxygen. And the proton is becoming partially positive while the oxygen is becoming partially negative. So because oxygen is very electronegative, it sucks or pulls the electrons away from the proton, making that proton less shielded because it has less electrons around it because of induction, right? The 3 protons that are in fact equivalent, meaning they are shielded exactly the same, they are on a carbon. Carbon is not as electronegative as oxygen. So in fact, you have a little bit of induction, but it's not as much, right? So I'm going to draw the bond dipole between carbon and hydrogen. Carbon is a little more electronegative than hydrogen. So there's a little bit of a pull of these electrons in this bond from hydrogen to carbon, but you don't have a large bond dipole that you have here. So this is really a larger bond dipole in this bond compared to the smaller bond dipole here. So what we're saying is in the carbon-hydrogen bond, teensy bit of electron density is being sucked away from the hydrogen, but not a lot. In the case of the hydrogen on the oxygen is pulling a lot of electrons away from the hydrogen, making it less shielded, or we say it becomes de-shielded. We're going to use the words de-shielded versus shielded. So I would say that these protons are more shielded, or they are shielded, compared to this proton in red, which is de-shielded or less shielded. And what's going to happen in the NMR spectrum is we're going to get a signal for this proton and a signal for these three. Since these three are equivalent, they will give us only one signal because they're shielded exactly the same. But the signal we get from these three, the one signal we get from these three will be in a different location in the NMR spectrum than the one we get for the one in red. So what we are able to do here in NMR is say how many different signals we get equals how many different protons you have in your molecule. And there will be other things that we can get from the NMR spectrum besides how many signals, meaning how many non-equivalent protons. We're going to be able to get a lot of information from this, and we're going to talk about that in our next slide. Now, just to kind of, well, let me get my eraser here. Just to compare, let's throw out a different molecule here. How many different signals would we get from, say, ethanol? All right, that is the skeletal structure. Now I'm going to show a 3D structure of ethanol. And I'm going to see a CH3. Let me see if I can, let me bring this up just a little bit. So I have a CH3 fragment right here. That's this guy. Put that one in black. I have a CH2 fragment, and then I have a hydrogen, an OH group. All right? I am going to get three different signals from this molecule. I'm going to have these three protons on this carbon, on this methyl. They were all going to give me the same signal in the same location. So I'll get one signal for these three. Why? They're shielded exactly the same. This proton is on a carbon that is next to a methylene, and then next to that is an OH. So it would be in the same environment as the other ones on that same very carbon, that very same carbon. So these three hydrogens would have the same shielding when you put this molecule in an external magnetic field, in the NMR instrument. These guys in blue here would be in the same environment as well. So the two in blue are equivalent to each other, but they are non-equivalent to the ones in black that are on this other carbon. And check it out, these guys are neighbors. So they're actually going to talk to each other, and they're going to split each other's signals, and we can get something called splitting, which tells us even more information. It tells us how many protons are beside these two and how many protons are beside these three. And then we have this proton, which would be less shielded or de-shielded compared to the ones in blue and the ones in black. So we would have a signal for this proton, which would show up in a different location than the signal for these two. And the signal for these two would show up in a different location than the signal for these three. So we would get 1, 2, 3 different signals. Why? We have 1, 2, 3 different types of protons. These are in a different environment than the one in red and the ones in black. These in black are in a different environment chemically than the ones in blue and the ones in red. Since they are in the same environment as each other, they only give you one signal for these three, but a different one than these two. Because of the electrons surrounding this one are being sucked away, this is the most de-shielded, and it will show up downfield in the spectrum. These protons in blue are on a carbon that is next to an electronegative oxygen, so they will show up in a different location than these three. Even though these are carbon-hydrogen bonds and these are carbon-hydrogen bonds, the ones in blue will be slightly more de-shielded than the ones in black. Because look, the ones in blue are on a carbon that is next to an oxygen. Well, what is that oxygen doing? It's sucking electrons away from whatever is next to it because of induction. Electrons are moving towards the more electronegative atom through the sigma bonds. Now, the further away the carbon is, the less it feels that pull of electrons towards the electronegative atom. So less electron density is being sucked away from these hydrogens compared to these. These are kind of getting more electron density sucked away from them because they're closer to that electronegative oxygen. So the most de-shielded and the furthest downfield. These will also be more downfield compared to these. And we would get 3 signals. 1, 2, 3 for each non-equivalent proton. So you get 4 things from the NMR spectrum. You get number of signals. We've already talked about that. Number of signals shows how many different kinds of protons present. Let's jump back. In methanol, we would get 1, 2 signals because we have 1 type of proton and 2 type of proton. In ethanol, we would get 1, 2, 3 signals because we have 1 type, 2 type, 3 different types of protons. How are they different? Shielding. So we get different numbers because we have different shielding, and that ends up putting those 3 or 2 different signals in different locations in the NMR spectrum. Because of shielding, we get different numbers, and then those signals will be in different locations. So the number and location kind of go hand in hand here. These two are due strictly to shielding. So this is what we were talking about here. This is a better example of shielding here. Oops. Now, intensity. If we get, let's jump back, if we get a signal from these 3, a signal from these 2, and a signal from this 1, the intensity is going to be higher if you get a signal from 3 than you get from 2 or 1. So what we're going to get signals for the different types of protons you have. And those signals will show up in different locations, and they will also have different intensities. The more protons that generate that signal, the larger the peak you see in the NMR spectrum. All right? The lower number of proton, right? If you only have a signal coming from 1 proton, you will get a smaller peak. So check it out. If I have, let me do this. If I have a proton NMR spectrum, this is going to be my little page, and I'm going to have a scale here, 0 to about 12. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You're going to get different signals. I'm going to get a signal for this guy, close to 1. Right? I'm going to just put a line where my signal shows up in the proton NMR spectrum. Okay? Then the blue is going to be a little bit more de-shielded, so it'll be downfield. So down, field, upfield. More shielded upfield, less shielded downfield. So these guys would get kind of pulled toward... Oopsie. I don't want to do that. Let me do this. No. Okay, so these guys would be pulled downfield, 2, 3, something around 3 maybe, right here. And then this one is going to be 1, 2, 3, 4. It's going to vary. Just going to put it here. So you see 3 signals, different locations. So that tells me I have 1, 2, 3 different types of protons. 3 different protons, different shielding, 3 different locations. Now, in addition to number of signals and location, I'm also going to get intensity. The more protons you have, I have 3 here, right? I'm going to get a signal that has an area that is 3 times the area under this signal, because this is 3 to 1. And this is 2. So this ratio is going to be a 3 to 2 to 1 ratio for signal intensity. You can actually have the computer measure the area under the signals. So we have number of signal, location of signal, intensity of signal to tell you how many protons are generating that signal. And then lastly, there's going to be splitting. If protons have neighbors, right, these protons are neighbored by these. They will be actually split by their neighbors. Why? The neighbors have a magnetic field. The magnetic field of the neighbor can either be opposed or, aligned with or opposed, which will cause splitting if this proton is 1, 2, 3 bonds away from these protons. So this signal would actually be split by these 2 neighbors. So it wouldn't be a singlet, it would actually turn into a triplet. So you'd get like a zip, zip, zip type thing. These 2 protons are equivalent and they generate a signal, but their signal will be split by 1, 2, 3 neighbors because they are 1, 2, 3 bonds away. All right. Now, there's a deal where if you're a proton on an oxygen, splitting doesn't count. So they don't split, and there's a reason why, and we'll talk about that later. But since these guys have 3 neighbors, their signal gets split into 4. So we still get number of signals, we still get location of signals, and we still get intensity, right? The area under here would be 3 compared to 2 compared to 1. That would end up a singlet. But we also get splitting to tell you, hey, how many neighbors does this have? So if I have hydrogens that give me a signal, not only do I get a signal that tells me what type of carbon they're on and what type of environment they're in, but I also get like how many hydrogens. Well, I have 3 hydrogens that generate this signal. They're fairly shielded, so maybe they're on an alkyl-like fragment, and they have 2 proton neighbors on a carbon next door. So I get lots of information, lots of structural information, which will allow me to say, hey, this is what I think that structure is. So again, number, location, intensity, and probably the biggest thing is splitting to give you the actual structure. So the next slide, what we're going to do is kind of show you a schematic of an NMR spectrometer. And the slide after this, we're going to show you a picture. This is what an NMR spectrometer looks like. Okay, this looks like a bell. So you have in the instrument, in the NMR instrument, right? If you have an NMR at your college, you would have this instrument right here in a room, and surrounding it, you would have, there'd be some other pieces of equipment, but there'd be a computer nearby. And you would make sure, because this is a big magnet, a very strong, powerful magnet, you would make sure that there weren't anything around it that were attracted to the magnet. and you can't bring anything close to the magnet that would be ferromagnetic and strongly attracted to a magnet. So you wouldn't want any kind of metal pipes around, because that would cause problems with the magnetic field. Let me see. I see that battery on. Give me 1 second here, folks. Try to plug this battery in, because if not, problems will occur. All right, so here you go. You've got this big instrument. Basically, there's a magnet inside here. It's a very large magnet. There's a bunch of other things we're not going to go into. But we can drop our sample inside the magnet. We go over to the computer and we run the program. And after a moment, after a couple of 16 scans or so, we get a spectrum. And we'll talk about what you see in your spectrum. But inside this instrument is a magnet, right? So take a look at the instrument. That's this guy. There's a magnet inside here. It's a big magnet, and it's cooled with liquid nitrogen to very low temperatures to increase the magnetic field strength. So this is our magnet, and we drop a sample tube that contains our organic compound in that magnet. So to do that, you get a little piece of glassware. It's a fairly skinny tube. Let me see. They're about that wide. They're a little bit longer than this, but you can hold it in your hand. Almost, this pen I have is kind of thick, but it's almost the length of a pen, and it's almost the width of a pen. It's got a closed end and an open end. And you take a drop or two, a couple milligrams of your sample, put it in the opened end, and then you add something called NMR solvent. And then you have sitting at the bottom your organic compound in NMR solvent. So it's a solution, right? So there's a solution in the tube containing your compound, the one you want to determine the structure of, in NMR solvent. And then there's a little cap. You put a little cap on this thing. It's a weird looking cap. Right, like that. You take this glass tube that's capped with compound in NMR solvent, and then you put like a little spinner. The spinner is just a little weird looking thing as well. You take your tube and then you insert it into a spinner, and then you go to the computer, you press a button that shoots air through a small tube that runs through the center of this instrument. You walk up the ladder here. The air is flowing out of the tube. You place this setup in the hole at the very top. The air allows that tube with spinner to kind of float. You walk back down to the computer, hit a button. The air slowly stops, and then the tube slowly falls. You don't want it to just drop and break. It slowly falls as the air stops moving through the tube, and then it sort of collects in the center. And then that spinner will allow the tube to spin inside the center of that instrument, inside the center, which means it's inside a magnetic field. So this tube would be spinning inside the magnetic field. You would pulse it with radio frequency, which allows the spin flipping deal to take place. The detector detects the information from the spin flipping, and it gives you a spectrum, a printout. Let's see. That printout, let me see if I can go to this, and hopefully it works. I don't know. It might not. If it doesn't, then oh well. It does. Okay. The spectrum on the computer, it basically just looks like a little printout. So it gives you a scale. It's called the delta scale. And it can go from 0 to 10 or 0 to 12. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, there's 12. Okay. And you can actually print out the spectrum on a page. And what we get is something that you will see in your homework, in the thing. And this has been sort of truncated here, but we have an NMR spectrum for C11, C11H16. Yikes. So there's the molecular formula. Where do we get that from? Mass spec. Or elemental analysis gives us a molecular formula. So you take a liquid, it's an organic compound, you run it through a mass spec, you get elemental analysis, you get the molecular formula, but you have no clue of what type of structure you have here. You can run this through the IR to take a look at functional groups, but you're not going to get from the IR, unless the molecule is very simple, lots of information about atom connectivity in your molecule. So you take mass spec, IR, and you combine it with NMR, and now you can nail down the chemical structure, the atom connectivity of your molecule. And sometimes you can actually characterize and determine the molecular structure based on just NMR alone. But it's actually best to have a combination of this mass spec, IR, NMR. So the first thing I would do, units of unsaturation. So units, number of carbon times 2 plus 2, right? So that's 11 times 2 is 22, 22, 23, 24, minus number of hydrogen divided by 2. So we have 24 minus 16 is 8, divided by 2 is 4. Okay, 4 units of unsaturation. Now, the next thing I would do is I would check out IR, but we're not going to have IR for this, and I would see, what type of functional groups I got. In this case, I can still get functional groups from the signals that I see in the NMR. So this is my NMR spectrum. There is a delta scale that we're going to talk about in 1 second that goes from 0 to whatever, out to 12. In this case, they stop it at 8 because there was nothing past 7 something. And I see a signal here at 7.2. I see a signal here at 2.5 on the delta scale, and there's a signal at like 0.9. And then there's an internal standard that gives me a signal at 0. This is for TMS. TMS. That's an internal standard. That's an additional thing that we put in that tube so we have a reference signal. And we're going to talk about that as well. So again, let's go back. You have a compound. You put it in an NMR tube, right? You drop that NMR tube into the NMR with the compound in it. You go over to the computer. You run the program. And then out pops an NMR spectrum. You see this first on the NMR on the computer screen. Then you can print this out and then take it wherever, or you can just keep it on a computer and save it there. But this NMR spectrum has signals that you can use to interpret and get the actual structure of your molecule. It is also very important that you have the molecular formula, because it's going to be really hard to get the structure without molecular formula. So molecular formula is very important. So if I have an NMR spectrum, I'm going to look for signals somewhere here. And those signals will tell me how many different types, right, of protons. The locations will tell me something about the shielding. And the splitting will tell me something about what is neighboring that proton in my molecule, right? So we can almost guess at what the proton NMR looks like based on our molecule, and we might do that later on. So here, remember I said that in the proton NMR spectrum, you're going to have an internal standard. Nowadays, we actually don't use tetramethylsilane or TMS. So tetramethylsilane is abbreviated TMS. And what that is it's a molecule that has a silicon and 1, 2, 3, 4 methyl groups. And these methyl groups are all equivalent, so they give us only one signal. We have 12 protons giving us one signal. And check out how shielded these protons are going to be. Why are they shielded? Well, silicon is not as electronegative as carbon, so carbon is more electronegative. So our bond dipoles show carbon pooling on the electrons. So we will get induction where electrons are being sucked or pulled towards the carbon, and that gives us an increase in electron density at the carbon. Guess what's attached to the carbons? These hydrogens. The more electrons you have surrounding your hydrogens, the more shielded they become, right? So you have lots of electron density here, helping to shield. More shielded protons, right, are upfield. Less shielded protons are more downfield. So shielded, de-shielded is pretty much the words we're going to use. So protons that are de-shielded go downfield in the NMR spectrum. Protons that are shielded are more upfield in the NMR spectrum. If you have something like the protons that you have in TMS, these guys, right, are going to be shielded. So what you're going to get is, in the NMR, a spectrum and there is going to be signals that come out of this baseline. If I only had TMS in my sample tube, I would get only one signal at 0 ppm on the delta scale. We're going to talk about the delta scale in a minute. If I put something else in here, I would get other signals as well coming out of the baseline. If my sample that I'm showing signals for in blue is in there in a greater amount than TMS, what you're going to get is you're going to get a little blip here for TMS because you just have a teensy amount of that as your reference. And you can say, okay, hey, I know that's my TMS right there, and I'm going to reference everything to TMS, and I know that TMS is at 0 ppm on the delta scale, and everything else is referenced to the internal standard, which is TMS. Nowadays, we don't use this. and we use our reference. The reference that's used is actually the NMR solvent. So you might have deuterated chloroform, which gives you a little signal at like 7.2 ppm for CdCl3. So nowadays, you're going to use some kind of NMR solvent as your reference. In the old days, they used TMS as your reference. Either one's fine. You can even use both. It's not a big deal. The only bad thing about TMS is it covers up anything near zero. So if in fact your sample, if you thought your sample was going to have a signal at zero, you probably wouldn't want to use TMS or close to zero. All right. So, all right. So on some of these, you're going to see TMS. See that? Now look at this. There's a little TMS right here. We're just going to ignore it. In other words, it's not part of our, in this case, C7H8O or C4H8Br2. It's just an internal standard that we've added in addition to the compound that gives us these signals. So take a look at the first page, and we're going to do a bunch of these problems together in a little bit. We have three spectra, three NMR spectra. So if we talk about more than one spectrum, we call it, we use the word spectra for NMR spectra. There's three different NMR spectra on this page. This is one NMR spectrum. This is, well, this is another NMR spectrum, and this is another NMR spectrum, but we have three spectra on one page. We have another three spectra on this page. We have another three on this page, and so on and so forth. Each spectrum is its own separate problem. That's one spectrum. Here's another spectrum. You get the idea, right? So what I'm going to do, what you're going to do is you're going to draw skeletal structure for the molecule that produces that NMR spectrum. Now, you want 11 carbons and 16 hydrogens in your spectrum. And if you think there's an aromatic ring in there, then you got to draw that aromatic ring. Maybe it's monosubstituted or disubstituted. We can actually tell from the splitting, however. And again, we'll go back and do that together. So I get number of signals, location of signals that tells me something about where it is, what type of carbon fragment those protons that generate that signal are on. And then I get splitting, and I also get intensity. Look, there's a lot of protons under this one, right? Compared to just a few or one under that one, and here. And what we get is we get integrations. So these little weird S-type things, we can measure that area under the peak, which is what the computer did. There's a computer program that will allow us to measure the area under the peaks. And we get a ratio of 9 protons to 2 protons. Wow, I really blew that one up. To 5 protons. So the peaks are integrated. That's what this little guy here is. And it's saying that the protons are 5 protons to 9 to 2 protons. So 9 plus 2 plus 5 is 16. We'll get to that in a little bit. But just to give you a kind of a preview of what an NMR spectrum looks like. All right, so we talked about chemical shifts. We're going to use something called the delta scale. All right, the delta scale. Remember when I said, 0 ppm, 1 ppm, 2 ppm, this is the delta scale. And the reason why we use this is that the signals might show up at different locations depending on the size of the magnet or the strength of the magnet. So you can have an NMR that has a 60 megahertz magnet. You could have another one that has a 100 megahertz NMR, and the other one, you can have another that has a 300 megahertz. You can have a 600 megahertz. If it's a 300, that's a stronger magnetic field than a 100 or a 60, right? So what's going to happen is, take a look. If I look at a 60 megahertz NMR versus a 300 megahertz NMR, if you take the NMR spectrum and you have a chemical shift at 120 hertz in the 60 megahertz, that same proton in the same molecule, but in a 300 megahertz NMR, will not be at the same location. It won't be at 120 hertz, it'll be at 600 hertz. This is a problem. If I'm using a 300 megahertz NMR and you're using a 60, and we're taking an NMR spectrum of the same molecule that should give us the same number of signals at the same locations, the hertz scale isn't going to work because we're going to be confused. I'm going to say that I have a signal at 600. You're going to say you have a signal at 120. It's going to look like we have different things here. So what we do is we take the chemical shift downfield from TMS. So there'd be TMS at 0 hertz, right? And in a 60 megahertz, you get the chemical shift at 120. So that's this guy. The shift, so the delta scale, is equal to the shift that you get downfield from TMS, which is 120 here. For this one, it would be at 600. And then you simply divide the chemical shift that you get in your NMR by the spectrometer frequency. So the spectrometer frequency is 60 here in megahertz. The spectrometer frequency here is 300 in megahertz. And you see that 120 divided by 60 is 2. And we're going to call this ppm. And then 600 divided by 300 megahertz is 2 as well, ppm. So now it doesn't matter whether we're taking the spectrum in a 60, 300, 400, 500, 600, 1,000 megahertz NMR. We're going to get the same chemical shift values if we're taking a spectrum of the same molecule in different instruments. So that's what the delta scale is. And then we showed you the delta scale here. So delta scale. 0 to 12. Now, in diamagnetic molecules that do not have unpaired electrons, you're going to see chemical shift values in the delta scale from 0 to 12. If you have a molecule that is paramagnetic, and we're not going to look at molecules that are paramagnetic. You can have chemical shifts that range anywhere from 0 to 200, even beyond 200. So the scale, the delta scale, doesn't cut off at 12, is all I'm saying here, okay? And when we get to C13, same deal, we will actually go from, on the delta scale, 0 to even past 200 ppm. And it's not that the C13s are paramagnetic. It has something to do with the gyromagnetic ratio of C13. But whether you're looking at a C13 or even a proton NMR, it's possible for both C13s and protons to go from 0 to 200 ppm. In C13, it's very common, even in diamagnetic. For proton NMR, you're not going to see anything past 10 or 12 for diamagnetic. This is the sort of the normal range of a proton NMR spectrum if the compound is diamagnetic. If it's paramagnetic in proton NMR, you can go out to 200. For C13 in a normal diamagnetic compound, normal is between 0 and 200. And it has to do with the difference between protons and C13s. So just kind of a look ahead, something that we're going to actually see. Let me see, here we go. So location of signals has a lot to do with shielding. So take a look at these molecules here. We have CH4, right? Methane. Basically, we have a carbon with 4 hydrogens on it. We're going to get one signal because all the H's are equivalent. And they don't have any neighbors, so you're not going to get any splitting. These H's are fairly shielded, and you see that you would get a signal for those H's. The delta here is going to be 0.2 ppm. So fairly shielded hydrogens, almost same as you would get for TMS. Now check out what happens if you put an electronegative group on the carbon that contains those protons. I'm going to put a chloro group here. Check out induction, right? That electronegative chlorine is going to steal electrons from the carbon because it's more electronegative. It pulls electrons towards it. So electron density sort of shifts towards the chlorine, away from the carbon, away from the hydrogens. And the hydrogens become de-shielded, right? They feel more of the external magnetic field than they did here. So these were shielded. These are now becoming de-shielded. And you see that the chemical shift goes from 0.2 to 3 ppm. For these protons, they give you a chemical shift of 3 ppm in the NMR. So if you had an NMR, right, let's go to our pretend NMR spectrum. There's my delta scale from 0 ppm. We'll go out to, I guess 12. And we would find that the signal that you get for CH4 is at delta is 0.2 ppm. The signal that you would get for these guys here would be at 3. So I'm kind of going to overlap, but I'm going to bring this one up above it so you can see. The signal for the protons, same number of protons. We'll try to keep it the same intensity. I'm sorry, they're a little bit different, but intensity really doesn't matter. CH3Cl, right? Now we would see, instead of the protons giving us a chemical shift close to 0, they give us a chemical shift of 3 ppm. So they go downfield. If, in fact, you add more electronegative groups, right? So if we do away with a hydrogen and we put yet another Cl group, that's more electron density being sucked away from carbon. Look what happens to the chemical shift value with 2 chloros on a carbon. The protons on that carbon generate a signal. Both protons are equivalent to each other. They give you one signal, there's no splitting, but instead of at 3, now we've got a signal at 5. And it's actually at 5.3. Okay, so CH2Cl2, 2 electronegative groups, bring that signal even further downfield. And if we turn this into CHCl3, where, go back here, instead of just 1 or 2 chloros, we do away with yet another hydrogen, and we put on another chlorine. That chemical shift of that lone proton now jumps to 7, goes way downfield to 7.2. See this? Different shielding. The more electrons that are being sucked away from the protons generating this signal become more deshielded and go further downfield. If you have shielding, you get signals that are upfield. So closer to 0 ppm is upfield, and anything like, down towards 7, 8 is downfield. 12 too is downfield. There are very few signals that you will see past 8. You do see aldehydes. The proton on a carbonyl of an aldehyde is down near 9. The proton on the oxygen of a carboxylic acid is at 12. Those are the only 2 that we really see way downfield. Aromatic rings tend to give you signals at 7. Protons on, of course, carbons that have got multiple electronegative groups are downfield at 5 and 7. Also, protons on carbon-carbon double bonds are downfield at around 5 or so. And we'll talk about all these different types of groups here in just one moment. So, typical values. So this is what we're talking about, right? This is the delta scale. If I have an alkane, let me see what I can do here with this. I'm going to do a couple of different ones. If I have an alkane, right? Alkanes will generate signals in the NMR that are close to about 1. You can have, however, CH3s, right? You can have CH2s, and you can even have, I should have erased, CHs. A CH3 gives you signals in an alkane at 0.9. If you have an alkane type fragment that is a methylene, a CH2, it's a secondary carbon now, right? It shifts that signal downfield a little bit, not much, still close to 1, but it goes to 1.3. If it's a methyne, a CH fragment, methyne, gives you a signal that's even a teensy bit more downfield from the methylene at 1.4. And it all has to do with the type of shielding you get. If you have a methyl that is next to or attached to a carbonyl, this methyl here, attached to a carbonyl, check out what happens to the signal. It's no longer at 0.9. It goes downfield to 2.1. This is a methyl ketone. See, these very common to have a methyl ketone signal exactly 2.1. The protons on a carbon of a carbon-carbon triple bond, 2.5. If you have protons on a carbon that is attached to an oxygen, right? These protons here, or even a chlorine or a bromine, these are electronegative groups. The oxygen, the chlorine, the bromine. They suck electron density away from the protons on the carbon that has a bond to these electronegative groups. So they become slightly deshielded, and you see that their signals range between 3 and 4. The proton on a carbon-carbon double bond goes way downfield between 5 and 6. Allylic, there's a double bond. Attached to that double bond is a carbon. On that carbon is an allylic hydrogen. That's the allylic position right there. Because it's next to, not right on, right? Not right on. This would be right on. And that is, delta here be between 5 and 6 ppm. This one is aldehydic, so it's going to be about 1.7 ppm. Aromatics, protons that are attached directly to a carbon that is a part of an aromatic ring. These guys go on the delta scale down to about 7.2, between 7 and 8, but very close most of the time. 90% of the time, 7.2. Aldehydes, like we said, between 9 and 10, usually at 9. The proton on a carboxylic acid, between 10 and 12, but usually at 12. Alcohols, the proton varies, and it's going to be a little bit rounded of a signal. It's not going to be like a spiky, pointy signal. Between 2 and 5, but variable. Never at just 2, never at just 3, never at just 4, never at just 5. It kind of depends on the molecule, and it varies between having that signal between 2 ppm and 5 ppm. So kind of really hard to tell sometimes. Same with the OH of a phenol. Same with the hydrogens on an amine. Variable and rounded of a signal. So why in an aromatic ring does this proton on this carbon of an aromatic ring, I'm going to redraw this aromatic ring. I'm going to draw it on its side. This is what we're looking at here. I got some double bonds here, right? So I got a double bond, double bond, double bond. And because these are double bonds, I have p orbitals. Here's our p orbitals right here, right? I'm going to draw the p orbitals now. P orbital, p orbital, p orbital, p orbital. In our picture, this blue thing, this donut-looking blue thing right here, is these guys above, and then the other one is these guys below. It's the molecular. They're showing a molecular orbital. I like to show this picture with these guys like this instead of the weird-looking blue rings. I like to do this, right? But these orbitals, these lobes that are overlapping, make up this donut below, and these orbitals up top make the donut up top. I like to just show it like this. But either way, if you have these electrons in the aromatic ring, those electrons create a magnetic field that you see here. So that ring that contains those pi electrons, it creates a magnetic field here in this ring. And in fact, the direction of that magnetic field that little ring generates inside the ring opposes the external magnetic field. See that? There's our external magnetic field. It can either be this symbol or that symbol with an H, with a B or an H. Inside the ring, the arrows are opposing the external magnetic field, but outside the ring, they are reinforcing, the external magnetic field. So if I have a hydrogen on a carbon, look where that hydrogen is. It's in that magnetic field that reinforces the external. So this proton actually feels more of the external magnetic field, thus it's shifted downfield. It's not as shielded from the external magnetic field because it's in a small magnetic field in this molecule that reinforces this guy. So it just shifts way downfield to about 7.2, anywhere between 7 and 8. But most likely for an aromatic ring, those protons that are on these carbons will be near 7.2. Likewise, if you look at a carbon-carbon double bond, so we got a carbon-carbon double bond, right? These protons on that carbon-carbon double bond, here's an R group here. These protons will be shifted downfield as well. Why? Because that pi bond there, same deal, right? We have p orbital, that creates a molecular orbital. In that molecular orbital, pi electrons creates a magnetic field. And inside, the magnetic field opposes. See this direction arrow is going opposed to that one. But outside, where the protons are, right? This magnetic field in green, the arrows are going with the external. So it's reinforced. That's why you see for protons on carbons of a carbon-carbon double bond, they're downfield. They give you a signal downfield, close to 5, 6. For alkynes, you see the triple bond. All right, this is a carbon-carbon triple bond. The pi system that you have for the triple bond creates an external magnet. So this little blue cylinder is because of the orbitals that give you that pi bond, and the other ones are here, give you this pi bond. So what you end up with is molecular orbital that kind of surround those two carbons and make like a barrel type shape or a cylinder type shape. And then you get this magnetic field from these pi bonds. You get a magnetic field generated that you see in green. So the pi bonds generate a magnetic field, just like the pi bonds in a double bond in an aromatic ring generate a magnetic field. Right? They generate their own the actual pi bonds generate a magnetic field, and these protons are in that magnetic field. And in this case, this proton that is a proton of a terminal triple bond, that guy here, right? That proton in a terminal triple bond is somewhat deshielded, but it's not really deshielded like you see the protons here, because these guys are right in that magnetic field, right? They're deep in this magnetic field, and they're in that part that reinforces the external magnetic field. Same with the aromatic ring. You see where this guy is? It's right in that part that is reinforcing the external magnetic field. With the alkyne, not really here, is it? It's not way out. It's not out here where it's sitting in an area that is reinforced. It's kind of neither opposed or reinforcing. So you see those generally at 2.5. So not really far down, deshielded, like the aromatics and the double bonds. Remember the aldehydic proton? If you have a carbon-oxygen double bond, you have a carbonyl. There's your R group. That hydrogen of an aldehyde is on a carbonyl. And look, it's right next to this pi bond. That pi bond, like a carbon-carbon double bond, a carbon-oxygen double bond has a pi bond. That pi bond will generate a small magnetic field. That small magnetic field puts that proton on the carbonyl in an area that's reinforcing the external magnetic field, so it gets shifted way far downfield because it is de-shielded. Because it's in this reinforced area, it's de-shielded. So between 9 and 10. OH, NH signals vary, like we said. And because there's hydrogen bond, the signal will be kind of rounded. Instead of a sharp signal like this, you will get more of a rounded, maybe not that rounded, but it'll be, geez, I can't. It'll be more like that instead of really sharp and spiky, okay? That rounding of the signal is kind of one indication that you have an OH or an NH. Obviously, in the molecular formula, you would look to see if there are any O's, or oxygens or nitrogens. Then in the proton NMR, you might be able to see that. So check out the carboxylic acid. Here we have an NMR spectrum. Goes from 0 to 10 ppm on the delta scale. And we have truncated off 11 and 12. Now, wow, yikes. If we were able to see 11 and 12, we would pick up this guy. So there is, I did this wrong too. Here is the delta scale, right? Right here, 0, 1, 2, 3, all about the 10, 11, and 12. And then here we have our signal, our baseline, right? There's TMS, right there. And then this is our signal coming out of the baseline here for these protons. Then we have nothing because there's no protons generating a signal. See this little kind of this staticky type baseline? There's no signals coming out, no signals coming out. And I'm going to kind of what did I do here? I'm going to kind of extend this, and then what we would see is this little blip right here. That's this guy. Now, in the old days, the graph paper would only allow you to print from 0 to 10 ppm. So on the graphing paper, you would see this very confusing little peak up here, and it would say offset 2 ppm from 10. So that means that out here at 12, you should see this guy. Nowadays, we have computers that kind of allow us to print whatever we want, and on our printout, we could print from 0 to 12 or 0 to 14 or whatever, and we would actually see that baseline extend from here all the way out and give us this peak where it should be. But this is just from the old days. And you notice that peak's rounded, right? Because it's an OH, and that is rounded because of the hydrogen being on an oxygen, and there is hydrogen bonding, which causes that. All right, so here is a molecule. 1, 2, 3, 4. 1, 2, 3, 4, 5. So C5, H something, and there's 1 oxygen. So we have 12 hydrogens. The first thing I would do is units of unsaturation, which would show 0 units. So I know I don't have any double bonds. There's no aromatic rings, and check it out. There's nothing at 7 or 5, right? Now, I get TMS here. It's just a little teeny little blip at 0. That's TMS. And I get one signal at about 1.2. I'm going to guess, ppm. And then another signal at about 3.2. So, knowing that I have 5 carbons and 12 hydrogens and 1 oxygen, and I only have 2 signals, that tells me that there is a lot of protons that are equivalent to each other. And since there's no splitting, I have a singlet and a singlet, there are no protons that are neighbors. So I have a carbon and a carbon with proton neighbors. I don't have those. So I don't have any of this situation where I have a carbon that has a proton next to another carbon that has a proton. These would be neighbors and they would split each other. I don't have any of that. So I have a spacer atom, like an oxygen, or even a carbon in between that doesn't have any protons on it, right? So they call these spacer atoms. And this carbon could be a spacer, if it doesn't have any protons on it. Maybe it's a carbon that has all carbon-carbon bonds. And then an oxygen can do the same thing. And then these would not split each other, neither would these. But if they were neighbors, they would in fact split. And then we will talk about splitting here in a moment. So here you go. You have this peak, which is way more intense than this peak. So if we do the integration, we find that this is 9 protons and this is 3. But we might not get 9 and 3. We might get a 3-to-1 ratio, right? 3-to-1 ratio. If I get 3-to-1, do I think that this is 3 protons and that is 1? No. Why? Because 3 plus 1 equals 4. I don't have 4 protons in my spectrum, in my compound. I have 12. So what about 6-to-2? That's another ratio that is the same as 3-to-1 or 9-to-3. Well, it can't be 6-to-2 either because 6 plus 2 is 8. I don't have 8 protons. I have 12. So the 3-to-1 ratio turns into a 9-to-3, which makes sense, right? If I see a 3-to-1 ratio of this peak to this peak, meaning 3 protons give us this signal, 1 give us that. I can't be 3 protons and 1. Can't be 6 and 2. It's got to be 9 and 3 because 9 and 3 equals 12. 9, 10, 11, 12, right? So usually we get ratios, but we turn that ratio into the number of protons depending on how many protons we see in the molecular formula. This is why it's very important to have a molecular formula. So I have only 2 different types of protons. I have these 9 and these 3. There's no splitting because there's no neighbors. So what I would do is I would look at a molecule that has 5 carbons, and I would say, how can I put those together? Do I do this? No, and you could put oxygen here, or 5 with an oxygen here, or 5 with an oxygen there, right? Or you could do it instead of an alcohol, you could do an ether. You could do 1, 2, 3, 4, 2, 3, 4, 5, like this. The problem with all of these is, look, I have proton neighbors. So there would be splitting. I can also count, 1, 2, 3, 4, 5. This molecule would require 1, 2, 3, 4, 5 different signals because this methyl with the protons would be non-equivalent to this methylene. This methylene is not exactly equivalent to this methylene. This CH2. This methylene is not equivalent to the other 2 methylenes, and this methyl is not exactly the same as that methyl. This is next to a methylene and another methylene, then an oxygen, then a methylene, then a CH3. This CH3 is next to a methylene, just like this one, but there isn't another methylene. There's something different here. So this is methylene oxygen. This is methylene oxygen. So these protons have to be shielded differently than this one. These would be a little more deshielded because they're actually closer to the oxygen than these, right? So you would get 1, 2, 3, 4, 5 different signals, not 2. This one, you would have equivalent methyls here and here. You would have equivalent methylenes here and here. and then you'd have a CH. So you'd get 3 different signals, and then 4 because of the hydrogen on oxygen. So that'd be 4 signals. You only have 2. 1, 2, 3, 4, 5. That would give you 6. 1, 2, 3, 4, 5. That would give you 6. So what you end up doing is you end up saying, all right, it looks like I have 9 protons. 1, 2, 3, 4, 5, 6, 7, 8, 9 that are all equivalent. Then I have 3 protons that are equivalent. So these 3 give you 1 signal, and then these 9 give you 1 signal. Check out this molecule here. So you have a CH3. So this carbon has 3 protons. You have a CH2. You have another carbonyl. You have an oxygen. And then you have this situation here, where you have a carbon and 3 CH3s. None of these groups have protons that are neighboring other groups. There's always a spacer in between, right? So I have a CH3 here, which gives me 1 signal. I have a CH2 here, which gives me another signal. And then I have 3 CH3s here. Let me turn this one red. That's 1, that's 2, and then these guys are 3 signals. Which ones would be more de-shielded? Which ones are more shielded? Well, look, these 3 methyls are on a carbon that's attached to an oxygen. That oxygen helps to de-shield, but these carbons are 1 removed from that oxygen. There's a spacer carbon in between here. So the protons in the carbon are a good distance away from the oxygen, but these aren't going to be at 0.9 ppm. They're shifted slightly downfield because of that oxygen, right? Because of induction to about, what is that, 1.45, between 1.45, something like that, 1.45 ppm, right? So downfield normal compared to a normal CH group. This CH3 is right at like 2.2. That's a methyl ketone. So very close to that 2.1 that we said for a methyl ketone. It's because of this carbonyl, causes that CH3 group attached directly to this carbon to be somewhat de-shielded, a little past 2. What about this? This is kind of like this guy, right? Because it is a methylene attached to a carbonyl, but it's actually sandwiched in between 2. Both of those carbonyls are de-shielding these H's. So this drops way downfield, all the way to 2.35 ppm. No splitting because there's no neighbors. Now, the first thing I could do is take a look at the molecular formula, find out there's 2 units of unsaturation, only 3 signals, no splitting. Some signals are further downfield than others, and then I could come up with some different types of possibilities for the structure of the molecule based on number of signals, molecular formula, and splitting. In this case, there is no splitting. And we talked about integration, right? In this type of graph paper, we looked at this molecule before, we can count spaces. This is this little, well, I'm going to do this in blue. This is this little S-looking integration thing that you see on the, so this in black is the signal, and then this guy is the integration. So I can measure from the bottom to the top, and you would count spaces, 1, 2, 3, 4, 5, 6. You could also get a ruler and measure in millimeters or centimeters, whatever you wanted. And then from that, from this to here, whether you measure or count spaces on your graph paper, if you have graph paper, you will get a number. So this is 6 for that. And then the other one is only 2 spaces. So this is 6 to 2. You could think of it as 3 to 1 and say that there's 3 protons to 1 proton. But look, this molecule is a C5H12O. So I wouldn't be thinking 3 and 1, nor would I be thinking 6 and 2. So I would have to keep the ratio, but go up to 9 to 3. And then you see the 3 and the 9. And 9 and 3 equals 12. That's how you determine the ratio and then figure out actually how many protons you have. The last thing we're going to look at is splitting, which tells us a lot of information. Spin splitting of non-equivalent protons on adjacent carbons. So there's going to be the 3-bond rule. If you have 2 carbons that are neighbors and they each have a proton, I'm going to put them in different colors. If these protons are close enough to split, they will split each other's signals. So instead of a singlet, you'll get something like a doublet or a triplet or a quartet or whatever. Here's the 3-bond rule. Bond 1, 2, 3. If they're 3 bonds away, if those 2 protons are 3 bonds away and they're non-equivalent, that's why I drew them in different colors, they can split each other's signal. So a proton gives a signal. If it's not split, it's a singlet. Just like you saw singlets here, 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 and here. All right? These would not give singlets. They would give doublets because this is next to a proton. Its singlet gets split into a doublet. Same with this one. If there are too many bonds in between the 2 hydrogens, well, let me do this. If there are too many bonds, 1, 2, 3, 4, there's no splitting. So this will give us splitting here. This will not give us splitting here. Okay? For protons to split, they have to be non-equivalent, and they have to be adjacent. And this proton with its little magnetic field will split the signal given by this one with its little magnetic field. And we're going to show how that happens. So check out this simple molecule here. What we have is C2, 2 carbons, H3, 3 hydrogens, Br3. There's only one way to connect 2 carbons, carbon-carbon bond. Now, you can put all 3 hydrogens on 1 carbon and all 3 bromos on the other one. That's one possibility for this structure. If that were the case, you would only get 1 signal, which would be a singlet. In this case, we get 2 signals, and then they just kind of zoomed in between 3.5 and 6 for the NMR spectrum. I'm going to go over here and kind of show us for the C2H3Br3 what we would actually see. 0. I'm going to go out to 7. All right, so we would actually see a peak at 4.1, and I'm going to, that's red right now, do a peak at 4.1. So we would have NMR signals jumping out of the baseline. If there was nothing here, just have TMS, this is what we would see. If we put this molecule in here, we get a signal at 4.1. I'm not going to split it yet. and we get another one in green at 5.7. Okay? 5. What was that again? 5. Come on. 5.7. 5.7. So if there were no splitting for this molecule, C bound to C, and we have some bromos, 2 bromos here, 1 bromo there, and then we have this guy, these 2. That's our molecule, right? 2 different protons, 1 in green, these 2 in red give us 2 signals. The red one would obviously be double the intensity of the green one because it's 2 to 1. And they show up in different locations because look, the green proton is more de-shielded. Look at induction. Look at the electrons being sucked away from the proton with the green compared to the only one electronegative group sucking electrons away from the protons in red. So these would be de-shielded, but not as de-shielded as the one in green. That's what we're seeing here, right? Don't know why it did that. So less shielded in red, more shielded in green. Less shielded in green, more de-shielded compared to the ones that are. So de-shielded, still de-shielded, but not as de-shielded. A little more de-shielded for these guys because there's not as much electron density being sucked away. So now let's look at splitting. The one in green, you see a triplet. Instead of a singlet, there is a bloop, 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 a triplet. The ones in red, both of these give you one signal. But because they have one neighbor, it's split into a doublet. Why a doublet for these 2 and why a triplet for these 2? Well, there's something called the N+1 rule that we're going to look at. N+1. If you have this proton, they labeled it as HA, right? And these protons gave you a signal. They were HB. They're the same. So HBs are the same. They're equivalent. HA is non-equivalent to HB. We're going to look at the N+1 rule to see splitting. If HA, this guy, has 2 proton neighbors, then N is equal to 2. It's 2 plus 1 equals 3. Its signal gets split into a triplet. The HBs, which give you one signal, have only 1 proton neighbor. That's this guy. So 1 plus 1 is equal to 2. That signal for HB gets split into a doublet. So why, if you have 1 proton neighbor, does your signal get split into a doublet? And why, if you have 2 proton neighbors, HA here has 2 proton neighbors, 1, 2, 3, 1, 2, 3, bonds away, and it gets split into a triplet? Well, here's the explanation. Take a look at the doublet, all right? These 2 give you a signal, which gets split into a doublet, because they have 1 neighbor that has a magnetic field. That proton generates a magnetic field, right? That's that little arrow. This is an H, by the way, right? That proton generates a magnetic field of its own, a little tiny little bar magnet-like magnetic field that can either reinforce the big field, right? Or it can oppose. So if these guys are sitting in an area of the molecule where they are being shielded this much, right? They're shielded to the extent where they give a signal at 5.2, or whatever it was. It was, 4.1. They are also by a proton neighbor that can kind of reinforce or oppose. So instead of the signal being right here, that's where it should be, right? That proton neighbor can exist in two states. It can either oppose, and if it opposes, what is it going to do to this signal? It's going to move some of that signal upfield. Why? It's opposing. So it's shielding these guys from the external by opposing. Or it can have that little magnetic field reinforce and align with the external, and in that case, this signal pushes downfield more because now these guys are next to something that is reinforcing, and it's making these more deshielded. So that signal should be here, but because these two generate a signal here, and they have one proton neighbor, that proton neighbor can be either opposed or reinforced. This signal disappears and turns into a doublet. So this guy right here and these guys. This guy has one proton neighbor, and that proton can either align, reinforce, or it can oppose. It has two options. There's only one of them, right? It can either go with the external, there's the external, either that or that. This is the NMR. This is the molecule that you put in there. These two protons generate that signal with that intensity. And they have a neighbor which can help to reinforce the magnetic field and shift some of the signal downfield, or it can oppose and shield it. So now, what do I want to do here? Now you don't get this right here. You get that. And you get a doublet. Now the doublet's going to look a little bit cleaner. It's going to be more like this. But in fact, it should have been right here, right down the middle. But because it has neighbors, I'm sorry, I did the wrong dang thing. There we go. It's the red ones that are being split by this, right? Because it has neighbors, it's being split into a doublet. Now, what I just did was I made a mistake, and it's a common mistake. And people see this one, and they call it a doublet, and they see this one, and they call it a triplet. But you have to look at these and ask how many neighbors are next to it. It's it's one neighbor plus 1 is equal to 2. That's your doublet. So 2 protons get split by 1 into a doublet. This guy, the one in green, right, gets split by 2 neighbors. 2 plus 1 is 3. So this is going to become a triplet. Why a triplet? Well, these 2 protons, 1, 2, they can either be aligned with or opposed. So imagine those 2 protons. I'm going to redraw this down here. C, and there's a green H. And then next to that, you have 1, 2. And you have all these bromos. Okay? This guy gives us this signal. These guys can either align with, both of them aligning with. What does that do to this signal? Well, it makes it downfield more, right? But they can do something else. So these protons, they can oppose both of them. That would do this to this signal. What can they also do? One can align with where the other opposes. That does nothing to the signal. Or they can flip-flop. One can oppose, one can align with. It does the same thing. So what you end up with is these two protons can both align with, or these two protons can both oppose, which shifts the signal upfield. These shift the signal downfield, or both of these protons can do this. One can go up, one can go down. And one can go down, one can go up. So there's two possibilities here. So we end up getting a triplet, 1, 2, 3, in a ratio of 1 to 2 to 1. You see the triplet is 1 to 2 to 1. Excuse me. Check out Pascal's triangle. 1, 1, 1, 1 to 2 to 1, 1 to 3 to 3 to 1, 1 to 4, 6, 4, 1. If you're a singlet, you got one peak. One peak equal intensity. If you're a doublet, look at this. One peak. Those protons can either be aligned with or against 1 to 1. 1 to 1 for a doublet. The peak intensities, or the peak heights for the doublets are the same. For the triplet, it's 1 to 2 to 1. Right? This is a ratio of 1 to 1. So we see how we get this 1 to 1, because there's an equal probability of this being up and that being down, or reinforcing and opposing. In this one, you have one option of both reinforcing, one option where they both oppose, and two options where one's up, one's down. So that's why you get doublets, triplets, and that's why the triplet will not have all the peaks equal height. There'll be a 1 to 2 to 1 ratio in peak height for those. And that's what we see in that spectrum. This guy is split into a triplet, 1 to 2 to 1 peak heights. The doublet is, right, these in red are split into a doublet with 1 to 1 peak heights. And then this is that same explanation that I gave for the doublets and triplets. Both spins up, both spins down, or reinforcing the external magnetic field, opposing, one reinforcing, one opposing, but you have two options here for that. All right, let's that's the n+1 rule. So if you're a proton and you have 0 neighbors, you're a singlet. If you're a proton and you have 1 neighbor, your signal gets split into a doublet. If you have 2 neighbors, you get split into a triplet. If you have 3 neighbors, a quartet, n+1, 3 plus 1 is 4. If you have 4 neighbors, 4 plus 1 is 5. It's a quintet, and then sextet, septet. Anything beyond that is a multiplet. But you can use the Pascal's triangle to look at the area ratios for that peak, like a 1 for a singlet, a 1 to 1 ratio for a doublet, a 1 to 2 to 1 ratio for a triplet, a 1 to 3 to 1 ratio for a quartet. So if you have a doublet, you get something that looks like that. If you have a triplet, you have a 1 to 2 to 1. If you have a quartet, it's going to be a 1 to 3 to 1, right? And then so on and so forth. We talked about the spin-spin splitting distance. That's the 3-bond rule. Long-range coupling we're not going to cover. So check this out. Here is ethylbenzene. You have benzene ring, then you have an ethyl group, CH3, CH2. I am going to get a signal for the aromatic protons. This is TMS, by the way, right there. I'm going to get one signal for these, one signal for these, and one signal for these. So 1, 2, 3 different signals. The aromatic shows up at 7.2, way down here, right? That's these guys. And it's a mess of things. These two are equivalent, but they're got one neighbor, so 1, 2, 3. That's a doublet. And if you zoomed in here, if you took this spectrum on a 600 megahertz NMR, you'd see the doublet that these two generate. This is like a doublet of doublets. So this is split by this guy into a doublet, and it's split by this guy into another doublet. So you get like a doublet of doublets, and then you get like a doublet for this as well. So it's kind of a mess for the aromatics, but you see a mess right here, a bunch of peaks at 7.2, and it integrates 5 to 2 to 3. I have a methyl right here close to 1. I have a methyl right here with 3 protons close to 1. And if you zoom in here, it's split into a triplet. So these 3 protons give me this signal, and they're split by 2 neighbors, N plus 1. 2 plus 1 is 3. So that methyl is split into a triplet. What about the methylene? It's attached right on that aromatic ring, so it is de-shielded a little more than it normally is, right? So the methyl is close to 1, but it's kind of de-shielded because it's close to the aromatic ring. So it goes from 0.9, where it should be, to like 1.2 because it's slightly de-shielded. The methylene should be at like 1.3, but it's way de-shielded because it's attached directly to the aromatic ring, and anything on that aromatic ring is de-shielded, right? Any protons on or close to the aromatic ring, these protons here would be in the benzylic position, so they would be de-shielded from their normal to about a 2.6 something. And they have 3 proton neighbors, so 3 plus 1 is 4. That's a quartet. So I'm going to put a Q there for a quartet, a T there for a triplet, and this would be an M for a multiplet. All of these would fall under this signal. 5 to 2 to 3. So I would get 8 carbons, and then I would get 10 hydrogens. I would do my units of unsaturation, and I would see there's 4. If I have 4, 3 double bonds in a ring, an aromatic ring is 4. I think an aromatic ring. I see something's out here at 7.2, so definitely aromatic ring. I see the integration is 5 to 2 to 3. So that means I have a phenyl with 5 protons on that aromatic ring. And then I have 2 more signals. One is a quartet, the other is a triplet. I can imagine what the shielding is based on the chemical shift values. And I would have a CH3 that's split into a triplet by a methylene, and a methylene that's split into a quartet by the 3 neighbors on the methyl. It takes a lot of practice, and you got to really slow down and do your N plus 2s. So let me do an N plus 2 for this one. T for triplet, CH3. N plus 1 has 2 neighbors, so 2 plus 1 is 3, triplet. I'm going to put the CH2 in blue here, and that's my quartet, Q. Well, it should be blue. Q for quartet. So N plus 1, right? It has 3 neighbors, so 3 plus 1 is 4. So I would want to see a quartet out of that guy. And then this would be a multiplet down at 7.2. 5 plus 2 plus 3 equals 10. 6, 7, 8 carbons, 4 units of unsaturation. I can be pretty confident this is my structure. Let's see. Do we have anything? Interesting. Let me see why. There we go. Good. Maybe this will get me to where I need to go. Got a couple more. Check out this example. I have a methyl 2.1 on a ketone. It's a methyl ketone, right? So I'm going to say that's going to be at about 2.1. If I look, I do have a 2.1. It integrates to 3. That's my methyl ketone. So they label this with an A. Right there. You see TMS right there. So don't worry about that. Just ignore TMS at 0. Methyl ketone, right? 2.1. Thinking methyl ketone. Then I have a CH that is kind of like a methyl ketone because it's attached directly to the carbonyl, so it should be somewhat de-shielded, shouldn't it? And it is. It's way down here. That's the signal. This is a zoom in of this. And look, this is a proton on this methyl that has no neighbors. Let me draw this. CH3s attached directly to a carbonyl. 1, 2, I can't get any proton neighbors here. This CH is attached to a carbon that has 2 methyls attached to it. So this proton has 1, 2, 3, right? It has all these neighbors, 3 bonds away. 1, 2, 3. 1, 2, 3 bonds away. It has n plus 1 is 6 plus 1 equals 7. It's a septet. So 1, 2, 3, 4, 5, 6, 7. That's what I see here. And it integrates to 1. So it's 1 proton that's split to like a multiplet or a septet. And then you have these 2 methyls that would be a doublet. And they're kind of almost normal, like a methyl should be 0.9, but this is a methyl on a carbon that's next to a carbonyl, so I'm thinking a little above 1, 1.2, 1.1. It's a doublet near 1. It looks to be at 1.1, so this makes sense, right? The methyls are the most shielded because they are furthest away from the group that de-shields things, the carbonyl. The CH and the CH3 that are directly attached to the carbonyl are de-shielded, right? They're shifted downfield to 2 and whatever this is, 2.5, 2.6 something, which makes sense. Now, if you had a CH next to a carbonyl and a CH3 next to a carbonyl, you wouldn't really be able to tell which is which unless you have some splitting, right? The methyl isn't split by anything because it doesn't have any neighbors, so it's really easy to see that guy right there as a singlet. And it's 3 compared to 1, right? So you got integration going for you as well. This is next to a lot of neighbors, 6 neighbors, so it gets split into a septet. That's how you can tell the difference between this CH and that CH3 as far as where it is in the NMR spectrum. The last sample problem here, we have a true problem. So we have C4H10O. Let's check out units. 4 times 2 plus 2. That's how I treat carbon. I'm going to divide everything by 2 and I'm going to subtract number of hydrogens. So 4 times 2 is 8, plus 2 is 10, minus 10 is 0. 0 divided by 2 is 0. No units of unsaturation. So I've got 4 carbons. I can attach the 4 carbons like this or like that. Maybe there's an alcohol in here. Maybe it's an ether. So maybe I've got my 4 carbons like this with the ether situation, or maybe I have an alcohol situation, right? Don't know yet. Let me look and see what the spectrum tells me. This is TMS, so I don't care about that. I have a doublet, a multiplet that's like a 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a no net. That's a doublet. This is a singlet, and this is another doublet. Okay, so I have 4 signals. Can't be this. 1, 2, 3, 4 with 10 hydrogens. Definitely can't be that, because this would only give me 1. These are equivalent methyls. So I'm going to dot that as 1. And then the 2 methylenes are equivalent. I only have 2 signals. So I can't have this guy. Gone. Can I have this one or this one? Well, let's see. That carbon would be a methylene. That would give me a signal. This would be a methylene that is non-equivalent to this methylene. That's another signal. Another methylene that's non-equivalent to the others, another signal. And then a methyl. 1, 2, 3, 4, and then your proton 5 on the OH. All right. Can't be that one either because we only have 4 signals. What about this guy? 1, 2, 3, 4. This is a possibility, right? Let's see. I would have this CH fragment, these 2 methyl fragments that are equivalent. So these would give me 1 signal. That would give me another. I would have a methylene that would give me a third. And then I have the H here that gives me a fourth. Well, let's see if this works out. The 2 methyls. The 2 methyls, CH3 and CH3. They're going to be close to 1. And they're split by a CH, aren't they? So N plus 1 for the methyls in black is 2. I'd need a doublet for these guys. Close to 1. And I do have a doublet close to 1. So that's perfect. And there should be 6 protons. And there is. If I do the integration, I would find there's 6 protons there. The CH, which is, a CH is a methyne, 1.4 is the normal. It's on a carbon that's attached to an electronegative. So maybe it's a CH that's 1.4 but shifted slightly downfield to like a 1.7, 1.8. But it should be like a multiplet, right? That CH has how many neighbors? 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 1 is 9. That's a no net. Look who we have here. We have a no net right where it should be. Not 1.4, but downfield a little bit because it's close to a carbon that contains an electronegative oxygen. So it makes sense. What about the methylene? The CH2. You can't split anything coming off of an oxygen. So that hydrogen doesn't split anything because it's on an oxygen. They can't talk. Protons on carbons can't talk to protons, neighboring protons on oxygens. So we don't get any splitting of the proton on an oxygen, and it doesn't split. It doesn't get split, and it doesn't split. So don't worry about protons splitting on oxygens. This guy is only split by protons on carbon, and it would get split into a doublet. And we see a doublet downfield at 3.4. And look, this is a carbon that is attached to an electronegative oxygen. It should get pushed downfield toward 3.5, and it should be a doublet. And we have that right there. And then we only have a singlet right here left, and that's there. And if we zoomed in here, we would probably see that that's rounded or broad. Right now it looks spiky and pointy. That's just because you're kind of zoomed out a little bit. But this makes sense that is my molecule for this spectrum. That's it for the PowerPoint slides. What we're going to do is we're going to do these 3 problems. So first one, we have this NMR spectrum, C11H16. We already did the units of unsaturation. We get 4 units of unsaturation. I'm thinking aromatic. Do I have aromatic? Yes, I do. Look at that. I could count up 1, 2, 3, 5. It's really hard to count, but you can also use a ruler. And do the integration here. I get 5 blocks counted. For this one, I got 2 blocks counted. So I got a 5, I got a 2 blocks, and I got a, I think a 9 blocks counted for this one. Should be a 9 there. It's hard to see. 9, 2, and 5. I can also measure distance, and that's what I did here. I showed the distance measured. I measured maybe millimeters or centimeters, I forget which, but I got 2.5 measurement here, a 1 measurement here, and a 4.5 measurement here. And the ratio, the whole number ratio, it could be a 5 to 2 to 9. 5 to 2 to 9. 9 plus 5 plus 2 equals 16. So I can believe the ratio of 9 to 2 to 5 is 9 protons for this signal, 2 protons for that one, 5 for this one. So I have a phenyl with something, and there are hydrogens, right? In the skeletal, I am not going to show the hydrogens here. Over here I do. So I'm going to erase in my skeletal structure. All right. Now, wow, 9 hydrogens singlet. 3 plus 3 plus 3 is 9, so I must have 3 equivalent methyls. This looks like a methylene, and then there's your 5 hydrogens on the phenyl. So let's see. Let's put a methylene here, and then there's my methylene, CH2, and these are my methyls. So I have a CH2, C with 1, 2, 3 methyls attached. No splitting because of the spacer, right? There's a spacer atom here which prevents splitting between hydrogens on this carbon and these carbons, right? And then these guys don't split either because they're too far away. So that's my molecule. That's what I would guess the structure to be. Let's go to the next one. C4H8Br2. So units, 4 times 2, 4 carbons times 2 plus 2. That's how I treat carbon. I'm going to divide everything by 2. Minus 8 hydrogens, and also minus number of halides, 2 bromides. So 4 times 2 is 8, plus 2 is 10. Minus 8 and minus 2 is 0. No units of unsaturation here. 0. I have C4H8Br, so I can put my 4 carbons like this or my 4 carbons like that. There's only 2 options here. Now, I'm going to do this with these guys here, and then these guys over here. The bromos can go on the same carbons. Br, 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 or they can go on opposite carbons. Here you can do Br, Br, or you could do Br, Br, right? And then you even have a bunch of more. You could put the 2 bromies on the end, like this. You could do the 2 bromines, one here, one here. You could do them like this, Br, Br. Here's all your options. But look, there's only 2 peaks in the NMR. That's TMS. This is downfield at 2. This is downfield at 4. So singlet, singlet, they integrate. This almost looks like, 1, 2, 3, 4, 5, 6 blocks to 1, 2. Is this a 3 to 1 ratio? Looks like it. 6 and 2 is equal to 8. So it looks like that's 6 protons and that's 2, just from the start. Okay. So with 2 signals, could we have this one? No. 1, 2, 3, 4. No good. What about this one? 1, 2, 3. Nope, because there's 3 signals. 1, right, these are equivalent and those are equivalent. This is a 2 signal deal. These two protons, these two methylenes are equivalent. These two are equivalent. But the splitting, right? This would get split into a triplet. This would get split into a triplet. So there's no triplets. Can't be that one. 1, 2, 3, 4. We don't have 4 signals. 1, 2 methyls are equivalent. These 2 CHs are equivalent. So this is a possibility for 2 signals, but this methyl would be split into a doublet. There's no splitting. That can't be. What about this guy? Methyl, methine, methine. Too many signals. So it can't be that one. What about this one? Well, I have a methyl, which is equivalent to another methyl. This is a carbon spacer, and this is a methylene, CH2. So I have 2 methyls, 6 protons, right there. Kind of de-shielded at 2, that makes sense. And then this methylene with 2 protons is de-shielded to 4 because it's on a carbon that is directly attached to a bromo, and on a neighboring carbon there's another bromo. So lots of induction here, a little bit of induction here. This makes the most sense. That's my structure. No splitting. The methyls and the methylene are too far away to split. Last one, C7H8O. So units, 7 times 2 plus 2. So that's 14, 16 minus 8 divided by 2. So that's 8 divided by 2 is 4. Is there an aromatic? Look at this. Yes, there is. So I'm thinking aromatic already. I can see that very easily in the proton NMR that I have an aromatic. That's TMS down here. I have another carbon. So that's 6 carbons, 7 carbons. And now I've got to say, do I have, is it like this? Or do I have this? Do I have an alcohol or an ether? Or is there a possibility for this to be like disubstituted? Where you have, ortho or something like that. Let's see. The integration is going to tell us, right? If I count up 7 blocks here, 3 blocks here, 1, 2, 3, and then 1.5 blocks here, which gives me a ratio of 5, whole number ratio, 5 to 2 to 1. So I can't have disubstituted because this integrates to 5 protons. This one, 2 protons, and that one, 1 proton. Look how rounded this is. Alcohol, right? Singlet that is rounded, no splitting, OH group, 1 proton. This one would have 2 protons. It's on an aromatic ring and it's on an OH, so everything's way de-shielded, right? 4.5, this varied, went to 3.8 or something, and this at 7.2. That's what I'm guessing right there. Okay, so you will do the rest. You will look at the molecular formula, get units of unsaturation. Look what we have here. Now we have some splitting. Don't be fooled with the TMS deals, right? I see TMS in all of these. These are some old school spectra. And then the rest are for you to do. And I think at this point you can do them. Thanks for watching. If you have any questions, shoot me an email. Make sure that you start working on this, on the D2L assignment, which is finishing the NMR spectra. And again, shoot me an email with questions if you have questions, or see me on the class discussions. Again, thank you for watching.